Hello and welcome back. We are continuing our journey about proteins, but today we are specifically zoning in on enzymes. So we're going to talk about what contributes to enzyme production, how enzymes can get denatured, what is their purpose, and specifically an enzyme that IB is requiring you to know about. So let's dive in with the basics. What is an enzyme? Well, it's a protein, like I've said like 5 times. It's a globular protein. Increases the reaction rate and lowers the activation energy. It's a catalyst. It makes reactions, like metabolic reactions, happen faster. The active site is this piece right here, this like funny shaped area on an enzyme. It's the area that would lead to a substrate being able to bind to it. So it's the area that allows a substrate, which is just something, a substance that is acted upon by the enzyme. The place where they connect is the active site. So how does it work? Well, substrates are dissolved and move randomly in water. Eventually, they're going to collide into an enzyme. When they collide into the enzyme and they bind with the active site, the enzymes can either bring substances together and build up something or break something down. The enzyme can weaken or strengthen the bonds within the substance or the substrate. This specific example is breaking down the bond. So you have the enzyme and the substrate, the enzyme-substrate complex, the enzyme product complex, and the enzyme and the products. You can see that it is being broken down here. So there's 2 versions of how the substrate and enzyme combine. There's the lock and key model, which is kind of what was used for many, many years. It's this idea that enzymes and substrates share a specificity. So there's an exact shape of the enzyme, there's an exact shape of the substrate, and so only specific substrates will be able to interact with specific enzymes. It allows for the enzymes and the substrates to have like such a small number of like the enzyme has such a small number of substrates that it can work with that it's just so specific. Over the years, we've kind of come to terms that this induced fit model might be a better explanation for how enzymes actually work. The enzymes do in fact have a specific active site shape, but it's not as rigid as the lock and key model suggested it was, and so it can undergo a conformational change. By going through that change, it allows for multiple different shaped substrates to actually bind with it. So even though, as you can see, this active site is not exactly the same shape as the substrate, it will go through a conformational change, and it will break down into the products just like we've seen other enzymes do. So this explains how an enzyme may be able to bind to several different substrates instead of just one. We talked about denaturation briefly last time, but we're going to talk about it a little bit more in detail. So denaturation is just a structural change in a protein. It changes the shape of the protein, which usually results in the loss of its biological properties. This is almost always permanent, but I don't want to use the word always because there are always exceptions, but typically permanent. Heat and pH changes are the 2 agents which may cause denaturation of an enzyme. So let's talk about temperature first. What is the effect of it and how does it impact it? So low temperatures mean insufficient thermal energy, which means low kinetic energy, which means molecules are moving slower. There's fewer collisions. When you increase temperature, you have higher kinetic energy, more frequent collisions. But when you increase the temperature too much, you're now disrupting the hydrogen bonds of the enzyme. And once those hydrogen bonds are broken, they're really, really, really hard to get put back together, which means the enzyme has now lost its shape, which means the enzyme is now denatured and unable to continue doing its job. When we talk about pH, it's a very similar situation. When you change the pH, you could potentially change the shape, which then, of course, diminishes its ability to bind to a substrate. All enzymes have an optimal pH, and moving outside of this range will always result in diminished rate of reaction. Whether you move to the lower end of the pH scale or the higher end, it will always result in a diminished rate of reaction. The third thing that can really affect enzyme production, product production through the use of an enzyme, is substrate concentration. So the more substrate you add into like a group of enzymes, obviously the more products you're going to make. The rate of reaction will increase because all of those substrates can bind to an enzyme. Initially, you're going to have more collisions, more reactions, but after a certain point, the rate of reaction will plateau regardless, because you have saturated the environment of enzymes, which means that it doesn't matter how many substrates are in this sort of environment, for lack of a better term. There's not enough enzymes, so you've hit the limit. You've saturated the environment. Now here's your specific example of an enzyme that we're going to talk about in so much detail you're going to hate it. Lactose intolerance. So lactose is the milk sugar, and it's normally broken down into glucose and galactose from the enzyme lactase. Yep, they all sound the same, I know. We'll get through it. So lactose intolerant people do not have a functioning lactase enzyme, so they are unable to break down lactose into glucose and galactose. You can see here that in America, there are few, in comparison to other areas of the world, few lactose intolerant people. But when you go to Southern Africa and East Asia, very high numbers of lactose intolerant people. So, what are some ways that we can avoid the lactose intolerant reaction? Well, there's lactose-free milk, which has its advantages, right? It's obviously a source of milk for lactose intolerant people. It can increase the sweetness of milk because glucose and galactose are sweeter than lactose. So if you already have them broken down in the milk that you're drinking, it tastes sweeter. If you're using this to make ice cream, you reduce the crystallization of that ice cream. You know, when you like leave the ice cream in the freezer too long and it crystallizes? Yeah, maybe you don't because you eat it fast enough, but I don't. So this like always happens to me. But glucose and galactose are more soluble, so less likely to crystallize. And you can have a quicker production of yogurts or cheese because bacteria ferment glucose and galactose more readily, more easily than lactose. So when we are talking about making lactose-free milk, we do this by immobilizing the enzyme. So when you make lactose-free, you're doing this by extracting lactase from yeast and immobilizing it in some sort of setup like this, where you have a bunch of immobilized enzymes, the lactase enzymes here. So you've immobilized them, you've separated them, they're in their pure environment. It's just the enzyme, and you pour milk containing lactose over it, and what happens is the enzymes break down the lactose, and then you end up with lactose-free milk at the end. And it's pretty interesting because separating these into like a pure environment is relatively new and pretty interesting. But it's pretty well used now. It's widely used in industry because putting enzymes in their pure state and not in a mixture like what's found in cells, right? We have like so many different enzymes, different cells, different molecules, different nutrients, all of these things just existing in our cells, but extracting just the enzyme and keeping them in their pure state makes them so much easier to use. So enzymes can be trapped in glass, in a gel, in alginate beads, in any capacity. But what are they used for? You name it. Easy separation, right? So the enzyme can be easily separated from the product to stop the reaction. So like you saw on that milk one, you just stop pouring the milk in and you've stopped the reaction. So easy separation. Recycling, that enzyme can be recycled over and over and over again because enzymes don't break down, so that's cost savings. increased stability. So immobilization increases the stability of the enzyme in response to pH and temperature changes. So although extreme pHs and temperatures will still affect it, it has a little bit wider of a range to allow it to kind of exist in temperatures or pHs outside of its optimum. And then higher enzyme concentrations. Of course, if you're separating them out into a pure environment, you can just add more. So you can increase the enzyme concentration, which just speeds up the reaction even faster. And then other commercial uses, we talked about making lactose and lactose-free milk, but you can also use it with pectinase, which is another enzyme. This acts on pectin, which is something that breaks down carbohydrates, but really pectinase is used in juice production. So if you are separating it out into its pure self, you can increase the yield of juice and the clarity of juice. So you don't get like if you've ever seen like really natural apple juice or something, it's a little bit murky. You can't quite see straight through it, but if you are just using this enzyme, you can actually make the juice pretty clear. And then protease breaks down proteins into amino acids, and you actually use proteases for stain removals, like on your clothes, when you dropped like stuff on your clothes. And so proteases help with that. So commercial applications, there's tons more out there, but these are two that I thought were interesting. That's it for this set of notes, so great job. I'll see you in class.